So on behalf of Mechanical Engineering Department, AD Patel Institute of Technology, I, Professor Baladat, welcomes you all in this first phase of STTP on Applied Computational Fluid Dynamics for Engineers. We'll start the session from the blessing of Mother Saraswati. With this, I pray Ma Saraswati to bless us all, and so that we could make this program successful. Now, I request our principal sir, Dr. Vishal M. Singh, to give us his blessings and start the program. Over to you, sir.
Good morning, one and all. Greetings from AD Patel Institute of Technology, CVM University. I welcome Professor Atul Sharma, all the participants from different colleges and states of India. I am thankful to AICT for sponsoring this STTP program that goes a long way for the faculty development initiatives of All India Council of Technical Education. I'm also thankful to mention the support offered by FDP coordinator Colonel Venkat from AICT in this regard. Computational fluid dynamics is one of the interesting areas, an emerging technology platform for analysis of different fluid thermal systems. It is also incorporating the fluid structure interactions. During this STTP, experts from esteemed institutions of India will be sharing their perspectives, thoughts, and opinions on this particular subject matter and enlighten all of us in this regard. I hope all the participants will be benefited by participation, and I am thankful in this regard. Thank you, and I wish a great success for this STTP and the efforts put in by the various coordinators.
Thank you, sir. Now, I would like to request our HOD Mechanical, Dr. Y.D. Patel, sir, to give us his blessing.
Very good morning to all. and I welcome Dr. Atul Sharma on behalf of Mechanical Engineering Department of ADIT. Let me introduce about the department. The Department of Mechanical Engineering was established since 2000, and department has 21 young, supportive and well-qualified teaching staff. The department vision is to nurture the universally relevant, knowledgeable and skilled human resource in mechanical engineering, and mission is to impart a value-based knowledge which students can utilize in the real world. The department offers industry relevance, hands-on practice and project-based training, and provides quality infrastructure and learning inputs. Mechanical department has invested more than 4 crores in state-of-art laboratories, more than 250 plus publications by the faculty members and students in reputed national and international journals, national and international conferences as well. Various webinars, STTP workshops are organized by department for emerging technology, entrepreneurships, innovations, and startups in support of forthcoming new education policy announced by the government, which will play a key role in creating a self-reliant India and open up the education sector for facilitating greater global exposure for our students. Every year, more than 40 students among the 120 of the department opt for the higher educations at the institute like IITs, NITs, and other countries like Canada, USA, Germany, Netherlands, and Australia. Department has 3 PG programs: CAD/CAM, Thermal Engineering, and Renewable Energy. All the participants are welcome at Mechanical Engineering Department of ADIT campus. I am sure that all of you have a fruitful interactions during this STTP with eminent personalities. I once again welcome you all for all the days during the STTP. You must interact and make all the sessions more interactive. And whenever the situation is favorable, I welcome to visit the Mechanical Engineering Department of ADIT. Thank you all.
Thank you, sir. Now, I would ask Dr. Mitesh Shah to introduce our expert for this session. Over to Mitesh Shah.
Very good morning to all. It's my pleasure and privilege to introduce today's speaker, Dr. Atul Sharma sir. Dr. Atul Sharma sir is currently serving as a professor, Department of Mechanical Engineering at IIT Bombay. He has completed his PhD from IIT Kanpur in 2004 and his master's from IISc Bangalore in 1998. His area of specialization is mainly computational fluid dynamics, development, application, and analysis. Computational multi-phase dynamics, development, application, and analysis. He is also involved in computational multi-fluid dynamics interaction. He has more than 20 years of teaching experience, including research projects, in which 10 he has already completed, 3 are under progress. He is having a projects of total funding worth rupees. He is involved in research guidance of 3 postdoctorate fellow, 28 PhD, and 35 MTech students. He is a renowned CFD consultant. He has been delivered various expert talk and series of invited lectures in various reputed colleges and universities across nation. He is a peer reviewer for more than 20 national and international journals. He has received various awards, including Departmental Award for Excellence in Teaching in Department of Mechanical Engineering at IIT Bombay, in recognition of significant contribution to the teaching activities of the Institute in 2019. He is the author of book Introduction to Computational Fluid Dynamics, Development, Application and Analysis under John Millay and Sons Publications, and 13 edited book chapters, in which 5 as a single author. He has 70 journal publications in 28 different journals and 75 conference publications. In addition to the regular academic courses taught as a part of his duties as a faculty member at IIT Bombay, organized and participated in continuing education programs for the industry and academia. These efforts are to train people in the field of computational fluid dynamics, including under the Indo-US collaboration for engineering education, under the National Mission on Education through ICT, Quality Improvement Program, TQIP 2 sponsored courses, continuing education program CEP, and short-term courses conducted for industry and academia. It's really a good opportunity for everyone to hear an eminent speaker like Atul Sharma sir from IIT Bombay. Sir, once again, Department of Mechanical Engineering, ADIT, welcome you. Thank you. Thank you very much. Sorry, mic is over to you.
Sir, you are not audible.
Sorry.
Now,
Yes,
Yeah. Thanks, Professor Bala, for the invitation and the kind introduction. You are able to hear me properly?
yes, sir.
Okay. It's indeed a matter of great pleasure for me to share whatever I have learned in the field of computational fluid dynamics. It would have been better if I had met all of you in person and interacted, but there are certain advantages in this online platform. But the most important thing is not the delivery, but the learning. So it's not more important what I say. What is more important that I always give importance is your learning. So I would like to draw your complete attention, especially in the online mode. We are distracted in many ways. So I look forward to your attention and wish and hope that whatever I've learned, I can share with you and it can benefit you in a great way. So with this brief, can I get started with the lecture, or is there anything left from the inauguration?
Please start, sir. Again, sir.
Okay, so let me share the screen. Professor Bala, I will ask you in between, everything is okay, just for confirmation before I go ahead. If I'm presenting, and you're able to see my screen?
Yes, sir. Yes, sir.
Okay. I welcome all of you to the AICT sponsored 5 days short-term training program on applied computational fluid dynamics for engineers. This course is organized by Department of Mechanical Engineering, A.D. Patel Institute of Technology, Vallabh Vidyanagar, and the course coordinator are Dr. Vishal Singh, and the course coordinator are Dr. Mitesh Shah and Dr. Baladar. So I welcome all of you to this first lecture of this course. This is a 5 days lecture, and I'm happy to see that there are a lot of distinguished speakers for this course. The title of my today's lecture is Role and Need of CFD for Engineers. Note that this subject is a very important in present day context, because nowadays we say make in India, make for world. So note that when you learn this subject, you can develop a product. You can develop a product which is like an app. It's an application software. This app development involves physics, chemistry, maths of your school education. This involves the core subjects of your engineering like thermodynamics, fluid mechanics, heat transfer, solid mechanics, and so on. So there is a lot of importance of this subject. However, one of the things which motivates me to propagate this subject or motivate me to make this subject easy enough, and for that I have opened up a YouTube channel called as CFD Made Easy. So I am motivated by the fact that this course is so important, and in various undergraduate curriculum, this course presently is either in final year, and the reason is that the faculties or student feel that this is an advanced course. So my motivation is to break this barrier, and my motivation is to make this subject easy enough so that it is taught in 4th or 5th semester of engineering curriculum. Because note that we talk of skill development, especially nowadays, with great pride and importance. But if this is the course which can train, which can impart the computational skill, but if we push this course as a difficult course to the 7th or 8th semester where students are busy in the placements and other activities, other competitive exam, then I think the purpose is defeated. This has my motivation to make this subject easy enough so that it is taught early in the curriculum. So in this lecture, I'll highlight what are the steps which I had done to make this subject easy enough, and to discuss the role and need for CFD for an engineer. I'll start with what is CFD, how it works, and finally I'll discuss the importance of this subject, where I discuss the role of CFD in more detail. So, Mr. Bala, everything is fine?
Yes, sir.
I would request to mute the mic of all.
I request every participants, please mute your mic, just to avoid any disturbance.
Thank you. So I'll first start with what is this subject, and so whenever you want to learn any subject, there are 3 questions which comes to your mind: why, what, how, and why. So I'll try to answer these questions while discussing the role and need of CFD. The first question: what is CFD? If you see various books of CFD, there are various definitions. So I have come up with this definition. CFD is a computational method of scientific and engineering investigation of a fluid dynamics problem. Note that whenever we investigate any problem, we not only investigate as an engineer, but we also investigate as a scientist, because we as a human being are always not satisfied with certain observation. We always have certain inquisitiveness where we try to understand why something is happening. So that answer why takes us to the quest of science. So the scientific investigation and engineering applications, both perspectives we keep in mind in our investigation. So the CFD is a subject which involves scientific and engineering investigation. And investigation, this where what we do here is focused towards fluid dynamics problem. And this subject is concerned with the development and application of a video camera-like tool. So we develop a product which is like a virtual video camera, which is a software. And then after development, we learn how to use it or how to apply it. Okay, so in this course is concerned with the development and application of a video camera-like tool. And once you use this, once you apply or once you use this software, you generate big data for the flow properties. The flow properties are velocities, pressures, and temperature. Okay, so once you generate a lot of data, in fact, you create movies. When you use this software, you can create movies where the movies, I will like to call it as a fluid dynamic movie. Okay, so when you use this software, you generate big data of variation of velocities, pressures, and temperature with respect to space and time. And once you have a lot of data and once you create a movie, the movie that you create through this software is a silent movie. Okay, so you watch that silent movie and you try to make a scientifically exciting and engineering story by watching that movie. So note that I will show you 2 types of movies. Movies which can give you scientific understanding, movies which give you about the engineering effect. Okay, so this is a subject which is a very powerful subject. With this you can develop a very powerful tool. So that's why its definition is little longer. So I'll repeat again, CFD is a computational method of scientific and engineering investigation of a fluid mechanics problem concerned with the development and application of a video camera-like tool. which is used for cause and effect based comprehensive analysis of the problem. Okay, so we as a human being want to use not only our mind, but also our body, emotion, energy synchronized in such a way that we try to understand scientifically and also want to improve engineering performance. So this subject makes you develop a great tool which has a great power by which you can do a lot of innovation. I have seen, in fact, I can give you an example. My first PhD student, Professor Sachin Paramane, who is working in an industry, he'll also be giving lecture in this course. So he will highlight a lot of industrial application. And I was earlier a CFD consultant when he was earlier in Compton Group. So I've seen this subject is greatly benefiting the industry. But so if you can learn this subject, you can develop this software and note that although companies are interested in using this software, but there are very few companies in the world which are making this software, and the cost is very high for most of the companies. So this software development can not only benefit the economic development of our country, but it can also take our country more closer to the developed country. So this subject has a great importance for Make in India, make CFD software in India for the world. Okay, now in the previous slide, I had given you one definition. From various perspective, various definition can be given. So in this slide, I am giving you another definition with another perspective. Like this is a subject where you do computational modeling, simulation analysis. Like if you want to use CFD software for flow across a car, then the first step is you create a solid model of the car, which involves, once you need to know the geometrical information of the shape of the car. Using the geometrical information, you create a solid model. And after creating a solid model, you take it to a software and do a simulation. Once you do a simulation, you get a lot of engineering, a lot of data corresponding to velocity, pressure distribution over the surface of the car. You also get certain lift force, certain drag force which acts on the car, which is related with the petrol consumption. Okay, so this is a subject concerned with the development of computer programs and its application for computational modeling. As I mentioned, we do solid modeling. This corresponds to the computational modeling. And then you do simulations where fluid dynamic simulations. And once you do fluid dynamic simulation, you generate big data, and with that data, you create certain fluid dynamic movies. And by looking into those movies, you do a job which is called as analysis. And this you can do for a natural fluid dynamics problem, and you can also do for a engineering fluid dynamics problem. Note that fluid dynamics problem, you observe a lot of fluid dynamics problem in nature. Like in last summer, we have a couple of cyclones in our country. One is Amphan in Calcutta, near to Calcutta, and another called as Nisarga, where Gujarat and Mumbai were affected. So those are like natural fluid dynamics problem, where in the sea a low pressure is created and it leads to the motion of the wave and the wind towards the shore. So these are like natural fluid mechanics problem. So note that CFD is not only used for engineering system, but it is also used for natural system, natural fluid dynamic system. So these are the two broad class of problems in which we use CFD for analysis: natural problem and engineering problem. How is the audio video quality, Professor Bala?
Yes, sir, it is fine. It is going fine, sir.
Okay. So I give a lot of importance to CFD. I especially want to highlight, even in my title of my book, I have emphasized that there are three aspects of CFD: development, application, and analysis. In development, you develop a product, which is like a virtual video camera, which is like a software. And then second thing is you learn to apply that software. And the third thing is, once you apply, you learn how to use the big data that is generated after application for a meaningful scientific and engineering story of a fluid dynamics problem. That comes in the analysis. So there are three things: CFD development, CFD application, and CFD analysis. Whenever we talk of a movie, there are two things. There are actors and there are characters. So first we need to understand, because later on the way I have given the definition of CFD, I have said that this when you learn this subject, you can develop a product through which you can create movies. Okay, so when I talk of fluid dynamic movies, in any movie you have actors and you have characters. So we need to understand who are the actors of the fluid dynamics movie. Now the actors of fluid dynamics movies are the flow properties like velocities, pressures, and temperatures, and the engineering information like drag force which acts on the surface of the car. Okay, so how these variables vary with respect to time. So we create movie corresponding to, let us say, if you create when the car is moving with certain speed, if you at each time instant, if you calculate the drag force, you can create a movie for how the drag force is varying with respect to time. You can also create movies for how the velocities, pressures are varying outside the surface of the car as the car is moving with certain speed. Okay, so note that the actor of this fluid dynamics movies are the flow properties and engineering parameters. What are flow properties? Flow properties you have studied in fluid mechanics. They are the properties which characterize the fluid flow. Those are velocities, pressures, and temperature. And there are certain engineering parameters also which we use as a character, like drag force, pressure drop for flow in a pipe, okay, lift force for flow across an aeroplane. So these are engineering parameters. So these two are the flow properties and engineering parameters are the actors for this movie. Whenever we talk, other than the actors in a movie, you also have a character. Now the character of this fluid dynamics movies are certain fluid dynamic phenomena that you have studied in undergraduate fluid mechanics course, like boundary layer, vortex formation, flow separation. So these are the characters with which we try to describe our movies. Okay. So if you have actors which are flow properties like velocities, pressures, and temperature, then we will call that movies as scientifically exciting movies. If the actors are engineering parameter, we will call it as an engineering relevant movie. So I like to differentiate the fluid dynamic movies as of two types: scientific movie, engineering relevant movie. Who are the actors in the scientific movie? Flow properties. What is the character in case of scientifically exciting movie? Flow structure. Who is the actor in engineering relevant movie? Engineering parameter. Okay. So later on, towards the end of today's lecture, I will show you this fluid dynamic movies. I will talk about the actors and the characters and discuss in more detail. Professor Bala, I would suggest that you can, I hope that if anybody has any question, he can write in the chat box. Is that option is there?
Yes, sir, it is.
Okay, so I request all the participants.
Please carry on.
I request all the participants that if you have any question, please do not hesitate. Feel free to write down in the chat box. And Professor Bala, I will in between ask you if there is any question and you can read it out and I'll try to answer. Is
Yes,
it
sir.
fine?
Yes, sir.
Okay,
Yes.
so yeah, so let us continue. So I started talking about the two types of fluid dynamic movies: scientifically exciting and engineering relevant movie. Now, as I said that we are very fortunate as a human being that like if you don't have food to eat, you have only one problem. Like if there is no food to eat for a lion, he has only one problem. If you give the food, then he doesn't have any problem. But as a human being, we have only one problem when we are hungry. But once our food is taken care of, note that we have thousands of problems. Okay, so the biggest problem of the present generation is we do not have to bother about food. So you have thousands of problems. So what I mean to point out through this is that we as a human being not only have stomach, but we have many other things like mind, body, emotion, and energy. We are always interested. We are like, if you consider flow across a car, let us suppose you have come up with a shape of the car, improved shape of the car, which is reducing the petrol consumption. You will not be happy or satisfied with your achievement, because as an engineer you have come up with a shape which is reducing the petrol consumption. Okay, but you also have certain other identity of human being where you are inquisitive enough. You would like to know why that particular shape is only reducing the petrol consumption. Okay, so we are always bothered about why. We are always wondered about certain happenings in nature. We always wonder about what we observe in nature. We always wonder about how birds fly, how fishes swim. This wonder and inquisitiveness gives rise in a scientific temper, and we try to investigate those problems. And although nature, as an engineer, most of the time you will observe that we try to mimic what is already in nature. Okay, so we have the best systems, most efficient systems in nature. And then as an engineer, we always wonder and get inspired by things in nature and try to mimic or replicate the natural phenomena. So what I'm trying to say is that when we create engineering relevant movie, like if you create a very good shape of the car, whose effect is that it is reducing the petrol consumption. But as I said, that you also have another identity of your human being. We are inquisitive in nature. So we are always interested in the cause, why particular shape of that shape is causing a reduction in petrol consumption. So this cause, the answer comes from scientifically exciting movie. And the effect comes from engineering relevant movie. And we want to make a story which involves the cause as well as the effect. Engineering parameters are the effect caused by the flow structure. Like if you consider flow across a car, the drag force is basically related with basically on the back surface of the car, there is a flow phenomena which occurs, which is called as flow separation, which leads to vortex formation on the back surface of the car, which is where you have low pressure region. So if you have large pressure on the front surface, low pressure on the back surface, there is a net force, pressure force, which acts along the opposite direction of the surface of the car. So this flow structure, flow separation causes the drag force. And if you come up with a very good shape of the car, you can, so this cause and effect are correlated. So when we use CFD, we try to make scientifically exciting movie for the cause, engineering relevant movie for the effect. And when we play these two movies together, we make a story which involves cause, that is science, and the effect, which is engineering effect. Together, we place synchronized these two types of movies, and then we make a comprehensive story for a problem. Now, let me take an analogy, because I talked about this subject as a saying that this is analogous to a virtual video camera. So let me draw an analogy. All of you have video camera, all of you have mobiles. So you are very comfortable. So let me take that example. Like if you take your mobile to create a movie, what you do is that you focus to certain region in space. Okay, so the size of, so when you create a movie, you focus to certain size of the region, and that depends on the focusing specification of your camera. Okay, like in your camera, there is certain specification, 5x, 10x. Okay, so what I'm trying to point out, the movies that you create through your video camera, the size of the region in which you focus depends on a specification which is called as focusing specification. Whereas in a computational domain, whenever we solve any problem using computational fluid dynamics, like if you want to simulate flow across a car, there also we have to take a region where car is somewhere inside that region. Okay, so the size of the computational domain is constrained by the boundary conditions that we apply for any CFD problem. Okay, so I'll discuss about this boundary condition a little later, but here I'm just pointing out that in your video camera, the focused region is you focus in certain region in space. Whenever we solve a fluid dynamics problem, we also focus to certain region in space that is called as computational domain. Now, whenever you go to purchase a video camera, one of the specifications is the pixel is given in terms of pixels. So what is pixel in your video camera? Whenever you click a picture, the picture corresponds to the color associated with the pixels per unit area. Similarly, in a computational, when you do a CFD analogous to pixels, here we have certain discrete points which are called as grid points. So what I am trying to say is that the video camera in CFD, the pixel for the video camera in CFD is what we call as grid points. And the quality of your picture that you create through your mobile's video camera, it depends on the the quality and accuracy of the quality of your picture depends on the spatial resolution which is given by the pixels, whether it is 8 megapixel or 10 megapixel. Similarly, in computational fluid dynamics, the accuracy of the results that we obtain depends upon the number of grid points. So your video camera quality depends on pixels. CFD accuracy, quality in CFD, we call it as an accuracy. The accuracy of the results in CFD depends on the number of grid points. And mostly in CFD, we take a non-uniform grid point distribution. The pixel distribution for your video camera is uniform. And in CFD, note that we are following a theory. This is a subject which involves only theory, no experiments. So the idea is that for any problem, as you keep increasing the number of grid points in CFD simulations, your results approaches asymptotically towards the true solutions. In your video camera, there is another specification with respect to time, which is called as frame rate. Frame rate basically decides that per unit time, how many pictures are created in your video camera. Similarly, in CFD, whenever we create movies, there at each time step we create a picture, but there is time difference between the two consecutive pictures. Here we call that as time step. So in your video camera, there is this temporal resolution which is given by the frame rate. Pixel in your video camera gives you the spatial resolution. Frame rate gives you the temporal resolution. In CFD, grid point gives us the spatial resolution, and time steps give you the temporal resolutions. The quality of result obtained by a video camera and a CFD software both depends on spatial and temporal resolution. Your mobile video camera depend on number of pixel specification and frame rate. CFD, as I mentioned, quality depends on number of grid point and time step between the two consecutive pictures. This analogy which I presented is not only applicable for CFD, but also applicable for computational solid dynamics, where you use finite element methods commonly, as well as many other software in science and engineering. Any question in the chat box, Professor Bala?
No, sir. Please carry on. I think we should follow the way that you talk it to the time, extent of time, and then at last I'll read out all the questions which have been there.
Okay, thanks.
Yes, sir.
Sounds good. So now let me take a comparison between an analytical solution and numerical solution. Now let me take you a simplest example. In your undergraduate course of, let us say, steady-state heat conduction, one-dimensional steady-state heat conduction with no heat generation in Cartesian coordinate system. So let us suppose the governing equation is d squared t by dx square is equals to 0. Now, what is the analytical solution for this problem? Let us suppose you take a 1D heat conduction problem, steady state with no volumetric heat generation. Let us say left wall is T1, right wall is T2. So then all of you know that the analytical solution is T minus T1 divided by T2 minus T1 is equals to x by L, which means the analytical solution of a differential equation is a function, because T minus T1 divided by T2 minus T1 is equals to X by L basically gives you a function, temperature as a function of X coordinate, T1, T2, and the thickness of the sheet, which is L. Okay, so T1, T2, L are given to you. And when you get a function, this is just an example. In 1D steady state conduction, you get temperature as a function of only X coordinate. If you consider in CFD, you cannot get analytical solution for a multidimensional problem. But in general, if you are able to solve the energy equation in, let us say, if you consider a 3-dimensional unsteady state heat conduction, then the analytical solution will be temperature as a function of X, Y, Z, and time. Note that in your undergraduate, not only in heat transfer and fluid mechanics, the governing differential equation that you have derived is a partial differential equation. And any analytical solution for a partial differential equation is a function. Like in fluid mechanics, the variables are velocities, pressure. In heat transfer, the variable is temperature. So you obtain analytical, whenever we say analytical solution, we mean velocities, pressures, temperature as a function of spatial coordinate and temporal coordinate. So the analytical solution, I like to call it as a numerical solution. CFD is a finite resolution virtual video camera. Analytical solution is a infinite resolution virtual video camera. Why I'm calling this analytical solution as an infinite resolution virtual video camera? Because in an analytical solution, you can substitute any value of X, Y, Z, and time. Okay, so the analytical solution, the fact that when you get a function as a solution, you can obtain solution which is like an infinite spatial and temporal resolution. But the issue is analytical solution is not possible for most of the real world fluid dynamics and heat transfer. Okay, this is like a very important problem. It is one of the most important unresolved problem in science and engineering. If you come up with an analytical solution, you will not only get the Nobel Prize, but it is as big as a problem that all the CFD companies all over the world has to close down. Okay, so this, although in your undergraduate course you have derived certain analytical solution, but note that those situations are very simple situations. When you go to an industry, you encounter multi-dimensional situations, unsteady situations, for which analytical solution is not possible till now. And for most of the industrial problems, we have to use CFD. And as in CFD, I have mentioned that analogous to pixels, we have to use certain grid points. So whenever, like in a room where you are sitting, let us say, if there is a fan and the air is blowing in your room, so if I have to do a CFD simulation, what we do is that we convert the infinite number of points inside your room to certain fixed number of points, which we call as grid points or analogous to pixels, and we obtain solution. Let us suppose we want to create the movie of flow of air which is generated by a fan in your room. Okay, then we will, when you use a CFD software, you obtain velocities, pressure and temperature, let us say, as a function of discrete point in space, which are like analogous to pixel grid points. So CFD is a finite resolution video camera, and the resolution of a CFD depends on the number of grid points that you take in your simulation. So we are not able to generate infinite resolution video camera, which is an analytical solution. We generate finite resolution virtual video camera for a CFD. Okay, so with this, I am done with the first question, what is CFD? Now let us go to the second question, how CFD works. There are, as I said, that there are three things of how it works. There are three aspects of CFD. CFD development, where you learn how to develop this product. CFD application, where you learn how to apply this product. Note that this CFD software is not as easy as learning how to use PowerPoint or MS Word. This software is pretty involved, And also note that this software cannot be completely automated, because when there are millions of fluid mechanics and heat transfer problems, so you cannot have a menu which involves all the fluid dynamics and heat transfer problem in the world, and you select that problem and it can solve your problem. There are many problems which are new also. So most of the time, the CFD software are such that the user has to be intelligent enough to use that software. He has to make certain decision. And in our personal as well as professional life, the decision which we take decides our fortune. So when you are using the software, the decisions that you take, there are many decisions you have to take. But unless you understand the background of the decisions that you make while using the software, you may take a wrong decision and you may end up with a colorful fluid dynamics, not the real world fluid dynamics. So the CFD application is very important. Many times, many students feel that why I am being taught how CFD development works. I am using a software, so why I need to understand how this software is developed. It is like whether you want to learn how to develop a car or how to run a car. Even if you are interested only in running the car, but if you know how the car is developed, probably you can become a better driver. Probably you can use the gears, clutches in a better way. So this is just a simple example, even if you are using a CFD software, but there is a lot of merit in understanding how the software is developed, because there are many choices that you have to make while using the software. And if you know how the software is developed, you can comfortably choose various options that is provided in the software, because you know the goods and bads of a choice that you are making. Okay, so now the last thing which I mentioned is the CFD analysis, because when you use a software, you generate a lot of data and how to use that data properly. So this is like a data analytic type of job you have to do. Okay, nowadays we have a lot of buzzword like big data, data analytics. So note that CFD involves both of them. So you generate big data when you use a software, because you generate data with respect to space and time for the velocities, pressures, and temperature. So big data is not only generated from the internet, but the big data is also generated by the physics-based simulation software. And then you have to do a data analytic job because you want. So this is what is called as CFD analysis. So in the end of the lecture, I'll discuss this analysis, CFD analysis, with the help of two example problems. So there are three aspects of CFD: development of CFD software, application of the CFD software, and analysis of the result for understanding of a fluid dynamics problem. Everything is fine, Professor Bala?
It's going well.
Okay, now there are 5 different steps of CFD development. So the CFD software development, there are 5 broad steps which I will discuss in the coming slide. This is the first step, which is like a pixel generation. Okay, so in our virtual video camera, which is a CFD software, the first step of the development is we have to generate pixels, which is called as grid generation. This is also called as pre-processing. Let me show you through a simple example. One of the simplest grid generation is, let us suppose there is a square region in which there is a fluid flow, or it could be a square plate in which there is some heat transfer, where the length of the domain is L1 and the height of the domain is L2. So the first step of a CFD software development, as I said, is the grid generation. Philosophically, I can explain you that the grid generation involves, the simplest of the grid generation involves equispaced vertical lines and equispaced horizontal lines, and the pixel that I generate corresponds to the centroid of the 25 small region. I have a bigger region, and I have, by drawing this equispaced vertical and horizontal lines, note that I have converted into 25 small regions which are called as control volumes. Now, when I define a pixel for CFD in a finite volume method, the pixels are located at the centroids of the control volume. So this is like 25 pixel generation for a problem which is in a square domain in which there is some fluid flow, or it could be a square plate in which there is some heat transfer. Okay. Here I have discussed philosophically, but mathematically, the grid generation involves determining the x and y coordinate of this yellow circles. Okay, because this coordinates makes us calculate the surface area and volume of the control volume. There are certain geometrical parameters which will later appear when we want to solve for temperature or velocity at this 25 yellow circles. So note that in CFD as a video camera, let us suppose we have generated this grid. So this is like a 25 pixels. So for 25 pixels, we will later on obtain solution with respect to time. At various time instant, 25 values of u velocity, 25 values of v velocity, 25 values of temperature. You can have same region in space, you can have same square plate, but you can have many heat transfer problems. So whenever you take a, let us say, heat conduction problem, it not only depends on the shape and size of the plate, but it also depends on another thing which is called as boundary conditions. Boundary conditions are extremely important, and the results are very much dependent on the boundary conditions. Like you have studied in your undergraduate course, if left wall is at 0, right wall is at 100. If you change the temperature of the left and right wall, the results changes. So note that we not only need grid points which are inside, but we also need the grid points which are at the boundary to apply the boundary conditions. So let us suppose these are the grid points at the boundary which are called as boundary grid points. So here I am showing you two types of grid points. Yellow circles are the pixels which are inside, which I will call it as a internal grid points. And the blue circles which are called as boundary grid points. So just to show you, there are 25 yellow circles which are inside, and there are 20 blue circles which are at the boundary. Now, whenever in the next step after grid generation, which I will show you, we derive the governing mathematical equations in CFD. Note that the governing equation in your undergraduate fluid mechanics is a partial differential equation. The governing equation in CFD is not a partial differential equation. It is a linear algebraic equation. So what does that mean? If I have 25 yellow circles, I will use a method, finite volume method, to develop 25 linear algebraic equations for this 25 yellow circles. I will use boundary conditions. I will discretize the boundary condition and obtain 20 linear algebraic equation for this 20 blue circle. So there are 45 circles. I will obtain 45 algebraic equation with 45 unknowns. So it's a closed system. You studied, so you know how to solve since your school days. If you have, let us say, 3x plus 4y is equals to 9, 5x plus 9y is equals to 10. Two equations with two unknown x and y, you know from your school days. But note that when you come to CFD, although here I am showing you only for, let us say, 25 yellow circle and 20 blue circle, that is the 45 circle, 45 pixel. But in actual fluid mechanics problem, note that we have to take an extremely large number of grid points. Now this basically depends on, like, if you want to create a movie for flow of air in your room, whether the fan is running in slow speed and high speed, the number of pixels or grid points that is required to capture the flow distribution varies. Intuitively, you can understand when the fan is running in high speed, you need more pixels or more grid points to capture the flow in the room more accurately. Okay, so what I'm trying to highlight through this is that in real world problem, the algebraic equation that you encounter is not manageable to pen and paper. You have, or calculator, you have to use computers. But the beauty is that later on I will show you that we will derive only one equation, and which is tailored towards recursive computation. Like just to give you an example, if you have a formula z is equals to x into y. If you are given x and y, if there are integer values, you don't need even calculator, you can get me the answer. If let us say x is 2, y is 3, you can tell me the answer quickly. But if I tell you that z is equals to 2.64, y is equals to 3.69, you will use calculator. But in CFD, it so happens that here also we derive an equation which is similar to z is equals to x into y. But the beauty is we write it in an indicial form. Like we write z is equals to I comma j is equals to x into I comma j, y into I comma j. Now what is this I comma j? These are like the data which is stored corresponding to this yellow circles. Okay, so we obtain equation, algebraic equation later on that we derive a single equation, but we use it in a loop. So it is tailored towards recursive computations. And since we are handling a lot of data, we have to store this data. When you have more number of pixels, you need to store the value of temperature, velocities, and pressure corresponding to those pixels. So we use a data structure, which is called as matrix as a data structure. And whenever you talk about matrix, any address of any element in a matrix, there is a row number and there is a column number. So the row and column numbers are the integer values. So these i's and j's which are shown here are corresponding to the running indices, which gives us the address of a particular pixel in a when you have a lot of pixels. So we apply pixel by pixel, we apply our equation pixel by pixel, and for that we use a loop. So we use this I and j as the data which corresponds to the running indices for the matrix as a data structure. So this are blue circles are boundary grid points or boundary pixels, and the yellow circles are the interior pixels. In your undergraduate heat transfer course, you have studied first, let us say, heat conduction in Cartesian coordinate system. Then you study in cylindrical and in spherical coordinate system. And you know that there are certain class of problems which are tailored for Cartesian, cylindrical, and spherical. But when you go to an industry, you encounter, let us say, conduction problem, which are neither tailored for Cartesian or cylindrical or spherical. Such class of problems are called as complex geometry problems. Okay, so here in this slide, I am showing you an example of a grid generation for a simple geometry and a complex geometry. Just to give you an example, if you have a square plate, which is as here, and there is a square hole. Now, in this case, there are two boundaries. Outer boundary, which is square, and the inner boundary, which corresponds to the hole, which is also a square boundary. Okay. So in this case, the simplest form is, so since the hole is square and the outer boundary is square, the inner boundary as well as outer boundary are made up of either horizontal and vertical lines. So this is a problem in Cartesian coordinate systems. So if it's a problem in Cartesian coordinate system, you can use the grid generation similar to what was discussed in previous slide. You can draw equispaced vertical lines, equispaced horizontal lines, and you can locate the grid points. Note that I am not locating the grid points inside the hole because I am interested in solving the heat conduction equation. I'll be only solving in plate. Okay, but since you have an inner boundary, you not only have this blue circle on the outer boundary, but now you will have blue circle on the hole also. Okay? Because at the hole also you will have to apply the thermal boundary conditions. So this is a problem which is aligned in Cartesian coordinate system. This is called as CFD problem in Cartesian geometry. But if you have a square plate with a circular hole or a circular plate with a square hole, then let us say in this case, square plate with a circular hole, the hole is corresponding to cylindrical coordinate because it has a constant radius, but the outer surface of the plate is in Cartesian coordinates. It's a combination of Cartesian and cylindrical, and in any case, this becomes a complex geometry problem. So in this case, the grid generation is a little involved, which is, we call it as a curvilinear grid generation, which is presented in detail in my book. So I'm just showing you the various control volume that we obtained after doing the curvilinear grid generation. Then we locate this yellow circle again at the centroid of this complex control volume. So these yellow circles are the internal control volumes, and these are the boundary control volumes in the outer surface of the plate, and these are in the hole. So here I have shown you the first step of CFD development, which is a pixel generation, I have shown you for a Cartesian geometric problem as well as for a complex geometric problem. After you have generated the pixels, which is grid generation, the next step is you have to use pen and paper and you have to derive the govern equation in CFD. Govern equation is linear algebraic equation, not the partial differential equation that you have derived in your undergraduate course. Because you cannot solve those partial differential equation for most of the industrial problems. Okay, so we have to do algebraic formulation in CFD. You did differential formulation in your undergraduate fluid mechanics transfer. In CFD, we have to do algebraic formulation. Classically, in CFD, they call it as a discretization method, and there are three methods which are called as finite difference method, finite volume method, and finite element method. Finite difference is one of the oldest method in CFD, but more recently, most of the present-day CFD software are based on finite volume method. And in my book, I have presented the finite volume method. Finite element method is more commonly used in solid mechanics as compared to fluid mechanics. And whenever you do this algebraic formulation in the second step, it results in one linear algebraic equation from each grid point. Okay, for yellow circles, we use any of this discretization method. And for boundary grid points, we commonly use finite difference method. So so whatever is the number of pixels, that many algebraic equation we obtain from the from this algebraic formulation. I would like to highlight that I have mentioned that one of my motivation in my learning experience of CFD, that I have been always motivated to make this subject easy enough so that it is taught into second year or third year in parallel with the undergraduate fluid mechanics and heat transfer problem. So I wanted to make this algebraic formulation very similar to like whenever you start, let us say, undergraduate heat transfer course, you start with the control volume. Okay, while if you see all the books in CFD, they follow another approach where they start with differential equations. So to make this subject easy enough, so that it is taught in second year, as early as second year, not in the final year, so that students develop the computational skill and they can probably start developing the computer programs by the time they reach this final year, and they can aim towards a startup for developing this software. So with that motivation in mind, I have started a YouTube channel also where I have uploaded the video lecture for the CFD course that I taught. So there are 20 hours of video lecture that I put in this channel. You can feel free to watch it later. Which is related with my book also. So I have come up with a new method of algebraic formulation, which I call as a physical law based. Now I also try to highlight PD free, because most of the undergraduate students or colleges, we have a private engineering colleges, and most of the students feel a little scared with mathematics. So I have tried to make this subject more of physics and less of math. I have tried to, because the way they are comfortable with deriving, let us say, heat conduction equation, they should be comfortable in deriving this algebraic equation for CFD. So I have come up with a simpler approach, which I call as physical law-based finite volume method. I'll discuss its philosophy soon. So let me discuss the finite volume method. But before that, I would like to take you along that in your undergraduate course, like in heat conduction, you take a control volume and you apply energy conservation law, and you write qx plus dx. First you write capital Q and then you convert into small q, calling it as a conduction heat flux per unit area, and then small q you multiply by surface area, and then you do one operation to divide by volume. Because when you convert capital Q into small q, the connecting term is a surface area. Now, why you do divide by volume? Because when you divide by volume, like you first get qx minus qx plus dx multiplied by delta y. When you divide by volume in 2D, delta x, delta y. So when you divide surface area divided by volume give you a length scale in the denominator. Okay, so like in your undergraduate course, when you write small q, you write, and when you do a balance, to calculate net conduction heat flux, you write Q small x minus Q small x plus delta x. Then you close it in a bracket multiplied by surface area, which is a delta y, because you have a vertical line, vertical surface of the control volume, whose length is delta y. And then when you divide by volume, you divide by delta x into delta y, where delta y cancels down from the numerator and denominator, and you get delta x in the denominator, and you take the limit of delta x tends to 0, and you get del by del x of qx. Okay, so note that any differential term that you derive, not only in heat transfer, but even in fluid mechanics, are the conservation law per unit volume. So in your undergraduate course, note that you apply the conservation law, and to get a derivative, you divide by volume and apply the limit delta x, delta y, delta z tends to 0. Okay, and you derive a differential equation. If you see all the CFD books, other than my book, what they do is that they start with differential equations. And this is where I believe that students feel that this subject is advanced, this subject is too mathematical. And because this book not only starts with differential equation, then it uses some mathematical theorem which comes like a bombardment to many, especially undergraduate students for most of the colleges in our country. So then they apply the Gauss divergence theorem. Okay, where certain volume integrals are converted into differential integrals. So what I'm trying to emphasize here is that in this most of the CFD books, they start with differential equation and then they do volume integral, which is like taking this differential equation and multiplying by volume. So I would like to point out that in your undergraduate course, you are dividing by volume, and almost all the CFD books are multiplying by volume. So my idea is why we have to first divide and then multiply. Why can't we obtain this linear algebraic equation, the same linear algebraic equation from the conservation law? So I feel that this conservation law, this physical law are like mother. And this differential equation is like elder brother. When computer came, we felt the need of algebraic equation. Before that, in fluid mechanics heat transfer, we were working with differential equations in theoretical fluid dynamics. Okay, so I believe that whether it's a differential equation or whether it's a linear algebraic equations, both these equations, the origin should be same. Okay, so this conservation law, which you have used in your undergraduate courses, we can start from this conservation law, which are like mother. We can use the same control volume that you have used. And instead of deriving the differential equations in your undergraduate course, we can teach this CFD course in parallel with undergraduate fluid mechanics heat transfer in 4th and 5th semester. Because I have come up with a procedure which is very similar to the way you can teach how to derive differential equation. You can, with the same school level math, you can teach them to derive linear algebraic equations. So I have come up with a physical law based finite volume method. Or note that this is PDE free. There is no differential equation. There is no Gauss divergence theorem. So this involves more of physics, less of math. However, I would like to point out the math that you use to derive these differential equations, you use a continuous math. But to derive this linear algebraic equation, you have to use another type of math, which is called as a discrete math. I also like to call it as a physical law and discrete math based finite volume method. Okay. So there is a slightly different type of math which we have to use, which I call as discrete math. And using this conservation law to the same control volume which you are comfortable from your undergraduate courses, using a discrete math which involves two approximations. And note the way this approximation, this discrete math I have presented in my book, and I had found that it involves school level math, and the approximations are very intuitive in nature, and it's much easier to learn, get a feel how these algebraic equations are derived to this approach, physical law based finite volume method, as compared to this approach. So note that you can feel free to use any of the approach, but I'm just trying to point out with this approach, probably you can explain the student in a much easier way. And since this involved school level math, it doesn't involve differential equations, which seems to be like a higher level math, which makes you to push this course to the final year. Okay, so using this simpler approach, you can derive this linear algebraic equation, which is the governed equation in CFD. So, Sir Bala, everything is fine?
Yes, sir. It is going well, sir. Please carry on.
Okay, so the first step is pixel generation. The second step is number of pixels, then many algebraic equation that we derive. Once we have derived algebraic equation, the third step is how to solve. Okay, you have also, you know how to solve algebraic equation like 3x plus 4y is equals to 9, 5x plus 9y is equals to 10. But note that here in CFD, it's not two equation, two unknown. Unknowns are not only x and y. There are not 2 pixels. You have, in real world problem, you have millions of pixels. And that too, it so turned out that, and all of you know that any algebraic equation you can convert into a coefficient matrix, unknown vector, and a constant vector. Now, to solve this differential, this system of algebraic equations, which is a huge, large number of equations, because you have large number of pixels to get an accurate solution. It has, when you see this equations, what you realize in your coefficient matrix, there are more zeros as compared to non-zeros. So if you follow, there are 2 methods of solving system of algebraic equations. One is called as direct method, and second is called as indirect or iterative method. So what I'm trying to point out is the solution of this system of algebraic equation is not straightforward. There are certain iterative methods that we commonly use not only in CFD but even in finite element method. So we commonly use certain iterative methods, and this is what we call a solution methodology. So here, this is a lecture which is more like an introductory lecture. So there is a lot of details which I'm skipping, but I'm just trying to make you understand and feel comfortable the philosophy. So I'm trying to show you with simple language also, trying to connect to you through your video camera pixels and this grid generation. And then I'm saying number of pixels, that many algebraic equation we derive in the mathematical formulation. And in the third step, we learn how to solve those. Okay. Now as far as solution is concerned, let me show you with a simple problem, with a simple example, and through some graphical animations, how do we, when we solve, what I mean by how we solve. Okay, so let us suppose this is a problem where this is like a first problem for CFD in heat conduction. What is the first problem? Typically, you've studied in your, let us say, undergraduate heat conduction. Probably the first problem that you've studied is 1D heat, steady state heat conduction with no volumetric heat generation. You said that there is a thin sheet in which there is a 1D conduction where left wall is, let us say, 0 degree, right wall is 100 degree. So this is some such like problem. Let us suppose you have a plate, left wall is 100, bottom wall is 200, right wall is 300, and top wall is 400. This is a 2-dimensional unsteady state heat conduction problem where these are the temperatures. So all the blue circles on the left wall as shown here are at 100. All the blue circle on the bottom wall are 200. All the blue circle on the right wall are 300. All the blue circle on the top wall are 400. Whenever you solve a CFD problem, especially the unsteady state problem, other than the boundary condition, there is, with respect to time, there is what it is given what is called as initial condition. Now, to make a story, I can say, let us suppose this plate is taken from a furnace where the temperature of the plate is 250 degrees centigrade. So all the yellow circles are at 250 degrees centigrade. And then I say that left wall is subjected to 100, bottom wall 200, right wall 300, top wall 400. So you know the first picture of your CFD movie. So you know the first picture from initial condition and boundary condition. The initial condition gives you the temperature of the yellow pixel, which is 250 degrees centigrade. And the blue pixel, the temperature you get from boundary conditions. So note that in CFD, the first picture of your movie comes from initial condition and boundary condition. And when we solve in what we call as solution in CFD, solution methodology, it is like this. Let us suppose this is the corresponding to the first picture where all the yellow circles are 250, left wall 100, bottom 200, 300 and 400. On CFD, when we solve, let us suppose if you are using one of the method of solution which is called as an explicit method. For that case, I am just showing you that if you are using a boundary condition 100, then this for all the picture, the left wall will always be 100. Bottom wall will always. Note that this temperature boundary conditions are time-wise invariant. Okay, so you need not bother about the temperature of this blue circle, how it will vary with respect to time. It is a time invariant boundary condition. So you know at this blue circle, left wall will at all for all picture it will be 100. However, the yellow circle values will vary with respect to time. In the first picture, all the yellow circles are at 250, but when we obtain an algebraic equation, let us suppose if you are using an explicit equation, we obtain an algebraic equation where let us suppose this yellow circle value is a function of 3 yellow circle of let us say first picture which are at 250, this blue circle which is at 100, this blue circle which is at 200. So what I'm trying to show you is a graphical representation of the algebraic equation that is used to solve. Now, when you use matrix as a data structure, it is very easy to know. Let us suppose you want to calculate temperature. This is I, j. So the same point of the previous picture will also be at I, j. This will become I plus 1, j. This will become I minus 1, j. What I'm trying to show you is that you know that the right column, the column number changes, but increases by 1. The left column, when you go, the column number decreases by 1. The row of the top one will decrease by 1. Okay, so what I'm trying to say is that if when you use matrix as a data structure and the row number, column number we store as the running indices, so we, as I had said earlier, that in CFD, when I have taken an example like z is equals to x and y, and I have said that here in CFD, we use an equation which is similar to z equals to x into y, but we write it in indicial form. So what I'm trying to point it out that in CFD also we derive only one equation, and that equation we use in the loop, where the loop is varying from 2 to 5. So this is I is equals to 2, j is equals to 2. When we go I is equals to 3, the same equation is solved inside the loop. This is I equals to 3. This is j is equals to 2, I is equals to 2. Okay, so this is all for j is equals to 2. This is all for j is equals to 3. So this is a graphical representation where you have a single formula which is in an initial form inside the loop, and the loop is varying from I is equals to 2 to 5, j is equals to 2 to 5. And what happens behind the computer is that it picks up 5 values from the previous picture and calculate the yellow circle value, single yellow circle value from the new picture. Okay, so the nature of the algebraic equation I have shown you here in a graphical form. For an explicit method, the nature is one value of the new picture is a function of 5 value of the previous picture, where we know all the data from the previous picture. So from the first picture, we obtain the second picture. From the data of the second picture, we obtain the third picture. And this way, picture by picture, we create the movie. So once you solve this, you obtain, note that movie for velocities, pressures, and temperature. But as an engineer, you're always interested in engineering parameters. Like for car, you are not only satisfied with velocity distribution, flow over the surface of the car, you also want drag force. Now to calculate this, we have another step which is called as to compute the engineering parameter, we have to do numerical differentiation, calculate the local value of engineering parameter, and we have to do numerical integration to calculate the total value of the engineering parameter. Just to give you an example, if we have solved the temperature distribution of yellow circle for the new picture, you can calculate for this blue circle, if you have to calculate conduction heat flux, this Qy, because vertical direction is y. So to calculate Qy, your formula is minus k dt by dy. to calculate dt by dy, once you've obtained the temperature distribution of this picture, you can take the temperature of this yellow circle minus temperature of this divided by the distance between these two circles and multiply by minus k to obtain qy of this blue circle. And then you can go to the next blue circle, calculate similarly. This way you can calculate qy on all these 4 blue circles. And once you know this qy, then you have to multiply with the surface area. When you multiply this qy with this surface area, you get total rate of heat transfer from this part of the surface. Similarly, you repeat for other part of the surfaces. So by numerical differentiation, you can calculate local heat fluxes, and by numerical integration, you can calculate total rate of heat transfer. Similarly, in a fluid mechanics problem, you calculate wall shear stress where you consider the velocity gradients, the normal gradient of tangential velocity, first to calculate local wall shear stress and then to calculate total shear force acting on the surface. Okay, so this way to calculate engineering parameter, there is a 4th step called as engineering parameter. Note that solution you obtain in 2 different steps. Then in this 3rd step, what you obtain through this, you can create scientifically exciting movies. You can create movies for flow property, but you cannot create movies for engineering parameter. Engineering parameter as an actor you calculate in the 4th step. Okay, so note that 3rd step gives you data and movie for flow, velocities, pressures, temperature. 4th step gives you movies for engineering parameters. Okay, now once you have obtained the flow properties and engineering parameter, you have obtained all the solutions, but the product development is not complete unless you do testing. So to do the testing, if you compare the result obtained from your software by a published analytical or a numerical solution, this is called as verification. And if you compare with experimental results, then it is called as validation. So the last step is testing, which is called as verification and validation. Okay, so Bala, we started around 10:15. Can I continue till 11:45?
Sir, actually, we have our next session starting from 11:45. So I think we can go up to 11:35 if you wish, but because next session is going to start from 11:45.
Okay, fine. So let me do a few things and then as per the timeline. So after discussing the CFD development, I am discussing the CFD analysis, where I'll take 2 problems. And in CFD analysis, we have to collect the spatial and temporal variation of flow properties and engineering parameters separately. Then we have to generate 2 types of movies, scientific movie, engineering level movie, and finally we have to make a story, as I mentioned earlier. So let me get into the problem. These are the problem. First problem is like if you consider heat transfer, this is a conduction heat transfer problem, and this is a fluid mechanics problem. Let me directly go to the problem and then discuss. Let us suppose nowadays electronic cooling is one of the biggest problem. Because as you want to purchase a mobile, you look into this. What is the review as far as the heat dissipation is concerned. So nowadays we have a lot of electronic components. We are trying to minimize its shape and size, but we are trying to maximize its functionality, which leads to more power consumption and the heat generation. So we have to dissipate the heat from this electronic equipment. So this is one of the heat conduction problem taken from the classical book on heat transfer by Inaugural and David. So this is like in this book, it has been presented that IBM had come with a heat sink, which is as shown here, where this electronic chip is connected with the aluminum plate, and this aluminum plate, there is a groove in which there is a micro channel in which the water is flowing. And in this case, if you do a simulation for the complete plate, it has been found that you get a symmetric results. So rather than doing for a larger domain size, let us take a simpler domain size where we use a symmetry boundary conditions at the top and bottom because this plate is very long. So the problem definition is such that from the electronic chip, this heat is coming in. Just to give you an example, the heat flux heat which is dissipated from the chip is 10 to the power 5 watt per meter square. And let me give you the dimension of this aluminum plate. The length of this aluminum plate is 20 mm, which is 2 centimeter. The height is 10 mm, which is 1 centimeter, and the size of the micro channel is 8 mm by 5 mm. So it's like it's a very small groove which is cut in this small plate. The plate dimension is 2 centimeter by 1 centimeter. And when you multiply this heat flux by the height of this plate, so there is 1,000 watt of heat, 1,000 joule per second, which is entering into this aluminum plate. Now this 1,000 joule which is entering at each and every second. Now the top wall and bottom wall is like an adiabatic wall, so the heat cannot go out. The right wall is insulated, so the heat cannot go out from here also. So the total heat which is entering into this aluminum plate, it has to go to the water, and there are three you can say path by which heat can go. It can go from this west wall or north wall or east wall. So note that the 1,000 watt is entering into this aluminum plate at each and every second, and it is taken by water. So now I will show you the movie. This movie, I will call it as a scientifically exciting movie. This movie corresponds to the actor of this movie will be the temperature. There is a blue color right now, which is corresponding to the initial condition. So the plate, this aluminum plate is initially at a temperature of, you can see from this color bar, the blue color corresponds to 15 degrees centigrade. Now when I'll play this movie, you'll start seeing the change in color. At this moment, the rate of heat transfer, what I'm plotting here is this Q, which I'm showing in the y-axis, is the addition of the heat which is entering into this microchannel. Okay, so this is QW minus QN plus QE. Okay, so the pink color which is shown here is the summation of the three. And what you see here is that as time progresses, this pink line is approaching towards 1,000. So the total heat which is entering, taken up by the water, initially it is less than whatever is entering. So if you apply thermodynamics, first law of thermodynamics, if more heat is entering then as compared to going to water, then there is a storage of heat. So there is a sensibility. The sensibility leads to increase in the temperature. But as time progresses, the water starts taking more heat, and a time comes when it takes all the heat. So if it is taking all the heat, then there will be no storage of heat. So there will be no sensibility, and thus temperature will stop changing. That we call as steady state. So let me play the movie. In the top movie, the actor is temperature. This I call a scientifically exciting movie. The bottom movie, the actor is I will show you a line plot which corresponds to, at various time instant, the amount of heat taken by the west wall, east wall, north wall, east wall by yellow color, north wall by green color, west wall by blue, and the summation of these three is given by the pink color line. So you can see around 5 seconds, the amount of heat which is taken by water is around 600 joule at this time instant. Okay, and you can see that the amount of heat which is taken by this blue and green, you can see the lines are very close. So the amount of heat taken by the west and north is more than as compared to east. The yellow color line is below this line. It is in the bottommost location. So the least heat is taken by this east, because the heat which is, I am also showing you the roadmap of heat flow, which is called as heat line. So you can see the roadmap is such that the heat is entering, leaving the chip, and when it is entering the plate, it is making a U-turn to reach to the east surface of the pipe, so east surface of this plate. Now and then there is a least heat transfer on the east surface as compared to this north and west surface. There is a larger heat because the heat can go directly onto this west surface and the north surface. So this is a movie of, you can see the red color is close to 32 degrees centigrade. So what you observe is the amount of heat taken by the water increases asymptotically and larger heat enters from the north and west pole as compared to the east pole. And finally, when you look into the steady state temperature, you observe that the maximum temperature that is reached is 32 degrees centigrade. So if you are in your mobile, in an electronic component, if the temperature is, maximum temperature is 32 degrees centigrade, then it is the safe for operation of the electronic component. So so in electronic component, we have what we call as hotspots, which gives us an idea. So this is an example for temperature distribution and rate of heat transfer, how it varies with respect to time. Note that the movie for the, this is a scientifically exciting movie. This is the figure 1.2 of my book. And this is the engineering relevant movie. More details you can find in the videos in this YouTube channel, CFD Made Easy. Finally, I'll just take a couple of minutes before I end. So in a fluid dynamics problem, if you consider flow across, let's suppose you are standing in a river and from the top you are looking like a circle and the bottom in the river is moving from left to right. So when it moves, it tries to push you along the flow direction, which is called as drag force. It also tries to move you along the transfer direction, which is called as lateral force. So note that the actor in a fluid dynamics movie, in a conduction problem, you only have temperature, but when you go to fluid mechanics, you have another actor, which is like a velocity vector. So this is a movie for velocity distribution. This is a movie where the color corresponds to pressure distribution, where the dark blue gives you the low pressure. So you can see on the back surface, let's suppose your body and the flow is from left to right. So on the back side of the body, you can see there is a low pressure. And the red color is a large pressure. So on the front surface, if you have a large pressure, on the back surface you have a low pressure, then you can understand that there is a net pressure force which is trying to push you. Okay, so similarly in the car, on the back surface, there is a vortex formation and there is a low pressure region. This figure shows you the blue color is giving you the lift and the drag force variation with respect to time. The yellow color is showing you the lift force. So these are the scientifically exciting movies. These are the engineering relevant movies. And I'll play the movie to give you an idea. Okay, more discussion on this is given in my textbook as well as the lecture video in this YouTube channel. I'll stop here due to the lack of time, and this is the figure 1.3 of the book. So the role of CFD is not only limited to creating scientifically exciting fluid dynamic movie of fluid properties, but also to create engineering relevant movie of engineering parameter for a unified cause and effect based comprehensive analysis of various fluid dynamics and heat transfer problems. And why there is a need to study this subject? Because this subject is of great importance to industry, research organization, as well as academics. This subject, I would say, has led to drastic improvement in the design methodology. I would say it has reduced the factor of safety used in the design processes. It has made more the design process as much more scientific as compared to the empirical in nature. And it is an excellent platform for innovation. For if you want to develop a new product, if you have come up with an idea, you don't need to convert your idea into a physical product. You can create a virtual product. You have the freedom of creating a virtual product, which takes less cost in a computer. So if you can come up with a new shape of the car, rather than generating a car, you can generate the car virtually through solid model, and then you can test your ideas. So it's an excellent platform for innovation. For an existing product, it's an integral part of an engineering study to improve the performance. It has led to more scientific as compared to empirical approach of design and development. Presently, CFD is used more as an analysis tool, although the industry wants to use as a design and optimization tool. Note that the CFD is not only applicable in mechanical engineering, but it is also applicable for aerospace, automobile, chemical, electrical, electronics. Nowadays, it's widely used in biomedical engineering also. CFD is taught as an undergraduate as well as postgraduate in various branches of engineering. And the increased importance of CFD development, application analysis in industry as well as research organization, along with lack of trained manpower, has greatly increased the importance of this course. Finally, I would like to highlight the companion textbook. This is the detail of my textbook, which consists of 3 different parts. This first part is like introduction and essentials. So it talks about very essential concept of fluid mechanics and heat transfer to learn CFD. It also talks about essentials of numerical methods. So if you have not taken fluid dynamics, heat transfer, and numerical methods, it tries to cover the very essential concepts. So it builds the foundation for this course. So in the YouTube channel, there are I have presented lectures for the topic 1 on introduction, the topic 2 on essentials, and then the topic 3 on computational heat conduction, topic 4 on computational heat conduction, and topic 6 on CFD on a topic 5 on finite volume method, topic 6 on CFD on a strategy. So there are 6 topics presented as video lecture corresponding to various chapters of the book, but the much more details are given in this book. And so in this book, you not only learn to develop the product CFD software for a Cartesian geometry, but there is a separate part to develop CFD code or a software for complex geometry on a curvilinear grid. These are the 3 parts. First part on introduction essential, the second part on CFD for Cartesian geometry, and the third part on CFD for complex geometry in the companion text book. The purpose of this book is to make you a CFD expert. As I mentioned, that I have started recently in this pandemic. I had to record the lecture to teach student here. So I thought, why not to share these videos freely to all the students anywhere in the country. So I started a YouTube channel a few months ago. So you can get more details in this YouTube channel. Although I'm giving a single lecture here, and this is the companion textbook. With this, I have come to the end of lecture, and I thank you for your attention. And you can ask questions here, but you can also feel free to send me an email for any query if you have in this subject. Okay, Professor Balan, back to you.
Thank you so much, sir. Actually, we are running short of time, or else I could have extended your session as per your wish, but I regret for the same.
So can we have a couple of questions from the audience?
Actually, right now, as I can see, there are at least no question right now, but I'll ensure that whatsoever questions are there, they will be emailed to you through me, and even I'll share your contact mail IDs and your official web page link with the participants too. And with this, I just would like to thank you for your excellent presentation and making it at a simpler level, because we all know how bulky and big this field of computational fluid dynamics is, and making it in such a simplified way is always took a lot of effort, and to have you as an expert, it is completely our privilege, and we really appreciate that you have given your time to us, sir. Thank you so much for all the efforts you have made for us and for this program.
Thank you for your attention. Thanks for the invitation, and I look forward for interacting with you in future also. Thanks a lot.
Thank you so much, sir. Have a nice day. So to all the participants, the next session will start sharp at 11:45, as our next session expert, Dr. Ajit Parwani, has joined us here on Google Meet platform. So I would like to welcome you, sir.
Thank you, sir.
And we'll just start your session at 11:45.